Hello, everyone, and thank you for the introduction. So, this work really begins with some observations. So, SAT solvers are very fast, they're very general, and they're flexible, but they are designed to solve a single SAT query extremely fast. So, here's a sketch of what I mean. We typically have a complicated system. Inside that complicated system, you'll have some interface that translates problems in your problem domain to propositional formulas. You'll send those formulas to the SAT solver. Your SAT solver will say this is satisfiable or is not satisfiable, and then you'll have some handler to translate those results back to your complicated system so that it can reason about the problem domain. And this is great, it works. However, if we zoom in on just the proposition side of this design, we'll see something like this, where we actually have a set of propositions, and between these propositions, there's lots of shared clauses, or there's a high likelihood of shared clauses. So here, feature model is shared, C1 is shared, etc. So what we want to do is we want to solve sets of SAT problems without constantly reevaluating the terms that are being shared. There has been work on this in the SAT solver community, and a major increase or benefit of that work is incremental satisfiability solving. Incremental satisfiability solving allows the end user to manipulate an assertion stack you can add a clause or you can remove a clause via a push onto the stack or a pop onto the stack. So if we have two propositional formulas, P and Q here, that share several terms, we can start our solver with an empty state. We can push the feature model. That'll add the feature model to the assertion stack. Then we can push C1 onto the assertion stack and continue all the way till we produce our result for P. Now, crucially, instead of starting with an empty state to solve Q, we can reuse the end state for P and pop C2 off, and then reuse that assertion stack to add C10 and then get our Q result. So what we've effectively done here is we have learned things in P and reused the state that was generated from P to solve a new propositional formula that is related called Q. This directly addresses the redundancy identified on the last slide and is efficient because it efficiently reuses results from previous runs of the SAT solver. So why not just use incremental solving? Well, not so fast. So we have our complicated system again, and we're using an incremental solver to direct its results, but this means that we have to handwrite a program to direct the solver for every result or every problem in our problem domain. So if our problem domain changes, the SAT solver doesn't know when to push, when to pop, or when to call isSat or gen model. And that means that if our problem domain changes, we have to change our interaction with the SAT solver. So what we wanted to solve in this paper was can we generalize and automate this interaction so that we don't have to handwrite these programs for each one of our problems. The way we will do this is we're going to take the incremental solver's implicit operations, the push and the pop, and we're going to make them explicit in the formula, and then we're going to automate that formula because we will know when to push and when to pop by just syntactically observing the formula. The way we'll do that is we will define a new logic called variational propositional logic. It's just propositional logic plus the choice calculus. Given two propositional formulas, we can synthesize a variational propositional formula where the only difference in this logic now is that we have a single new connective that we call a choice. Now, choices make it explicit what terms will be changing in the set of SAT problems and which terms do not change in the set of SAT problems. And so by making this explicit, we can automate the interaction with the solver. So I'm going to go over some variational propositional logic now so that we all speak the same language. So given our variational propositional formula, when we see a choice, we call the Boolean variable that indexes that choice, in this case A, capital A, a dimension. Anything that's not inside a choice, we call plain. And the things that which are inside a choice, we call alternatives. So in this case, C2 is our left alternative and C10 is our right alternative. Now to go from a variational propositional logic formula to a propositional logic formula, we will configure this choice. So given P or Q, if we set our dimension to true, then we will recover P by replacing our choice with the left alternative, C2. And if we set A to false, we'll recover our right alternative, which is C10 in this case. We call the associations between dimensions and Boolean variables configurations, and then we call the propositional formulas that result from being configured variance. Okay, I'm going to go over the variational SAT solving algorithm now, or formula. Given a VPL formula, we will solve the formula in 3 modes. So we will have evaluation, which will send terms to the solver underlying incremental solver only if it is safe to do so. We will have accumulation. When it is not safe to send terms to the solver, we still want to cache and combine them and replace those terms with pointers in the variational solver's memory. And then we'll have a phase where we explicitly remove choices, thereby creating new plain terms that we can then process with evaluation and accumulation. Crucially, only evaluation communicates with the incremental solver. Accumulation and choice removal only exist in the variational solvers at the variational solver level. Okay, so I'm going to go through a worked example of how the variational solver solves a formula. Given our VPL formula, we will call evaluation on it. Evaluation is going to find the feature model and the conjunction at the top level of this formula and send the feature model to the underlying solver. Then anytime we see a unit and replace it with a unit value, which I show here as a bullet, that indicates that the feature model has been sent to the underlying solver. Now, anytime we see a unit value with a conjunction in evaluation, we can replace it or we can remove it because things will be implicitly conjoined on the assertion stack. This will leave us with the right-hand side of this conjunction. We can no longer process this with evaluation because we cannot process disjunction in evaluation. So we switch to accumulation. Accumulation is going to create spaces in the variational solver's memory for each one of these clauses and replace them with pointers to that place in memory. We call these symbolics. And then it's going to seek to create new symbolics to capture all the plain subterms possible. So it'll find this conjunction on the right-hand side in the negation, replace that with a pointer representing that entire subtree, and then it will try to combine S1 and this symbolic we just generated to conclude in what we call a variational core. Now, given a variational core, we can move to choice removal, and we'll configure the variational core by removing the A choice. So when A is true, we'll replace C2, and we'll have C2 or our symbolic. And then when A is false, we'll replace the choice with C10. Now, evaluation will see a formula which is entirely plain here, which means the entire thing will be evaluated to a unit. And once we see a unit in evaluation, that's when we will call isSat or generate a model or satisfying assignment. The second point I want to highlight here is when we solve for the right alternative, A equals false, we will have cached the symbolic subtree, and so we'll have a cache hit leading to some performance improvement. So I'm going to go over our research questions now, at least 2 of them. The first question was, well, is this evaluation accumulation process actually faster for 2 real-world data sets? So we have 2 real-world data sets here. The automotive O2 had 4 versions, so it will have 4 dimensions, and then has multiple choices using those dimensions. Financial services had 10 versions, so 10 choices, and they varied in the number of plain terms, but the essential message is the same. We see about a 2x speed up just by automating the interaction with the incremental solver and caching on the plain terms using accumulation and symbolics. Our second research question was, well, we would expect then, as the plain terms increase in the number of total terms of a formula, then the variational core would be smaller. It would be reduced. Therefore, we would expect that if we have more plain terms in our formula, we will have a higher degree of speed up than if we have less plain terms. So we directly measured this by combining both of the data sets and normalizing the speed up and the plain ratio, and we find that it does indeed correlate. So this means that any way to increase the number of plain terms in a formula is likely to have observable speed ups when we actually run the solver. So it's highly valuable to increase the plain terms in the formula. Okay, so here's why I think you should read the paper. We started with our complicated system, and I've really focused on the propositional side of this, But remember, for each one of these propositions, we will also have some results coming out of the solver, and I have completely neglected the right-hand side of this. We do have an answer here. We formally defined variational models, but I don't have time to cover that in this talk. So I didn't cover the variational propositional logic equivalence rules and properties. I didn't cover variational models, and I didn't cover overhead. So if you're interested in this, I would ask you to read the paper or get into contact if you have any questions, because I think these things are quite interesting, and particularly I think variational models is a good contribution. The equivalency rules are important because from our second research question, we know that improving the plane ratio, or the number of plane terms in a formula, is important. And the equivalency rules for the logic allow us to do that by moving around choices. So in summary and in conclusion, we started out with a complicated system, and we wanted to automate the interaction with the incremental solver to give ourselves an easy way to use the incremental solver, so we didn't have to constantly handwrite programs to direct the incremental solver for our problem domain. We did this by defining the variational propositional logic, which allowed us to be explicit about when to push and when to pop and how to interact with the solver. Given the methods that we presented in this in our paper and in this presentation, we found that this does indeed improve our runtime compared to a naive use of the solver, and the benefit is that we did not have to handwrite any of the interaction with the solver. We only had to encode our problem set into a VPL formula. A limitation of this is that the VPL formula has to be known, which means you have to know the set of problems you want to solve beforehand. If you're interested, I would refer you to the paper called Variational Satisfiability Solving, and thank you for your time.